Welcome back. Let us continue our discussion by talking about periodic trends. Now, we've talked about periodic trends in the past, so this is going to be a little bit of a review, but we want to take our knowledge of periodic trends and we want to push it forward with now the knowledge that we have gained from the past, meaning that we want to think about things like orbitals, we want to think about things like electrons, interactions with the nucleus, the charges on the electrons, the charges on the nucleus. We want to give an explanation for the trends, not just list the trends so plainly. So that's what we're going to do. Let's get into it. We're going to start by talking about what I would say is probably the most straightforward trend, and that's atomic size. Another way to think about atomic size is atomic radius. Sometimes you have to kind of imagine that your elements are sort of like spheres, right? Almost like onions that have different layers. And that is what we do when we look at atomic size. So atomic size, the general trend is that as we go down and to the left on the table, the atomic size increases, which means that our largest friend on the table is francium. Now, a couple things to keep in mind is that when we have a cation, the cation is always smaller than the atom it derives from. And when we have an anion, it's always larger than the atom that they derive from. We can actually kind of see an illustration of this if you look into your book. Figure 10-4 kind of shows this. Say, for example, I'm talking about something like sodium. I'm going to kind of draw along here. Let's say that I have sodium, and sodium looks something like this. We're just going to pretend this is what sodium looks like. It's just a ball. And if we think about sodium's electron configuration, sodium has the highest energy level at 3s1. That is sodium. And if sodium were to lose that electron, it would become an ion, which is what it often does. When it becomes an ion, it looks like Na+. Now, when it loses that ion, it loses access to that entire third energy level, and it shrinks down to 2s2, 2p6, which means that it does not have access to that layer anymore. Again, it's like an onion where we peel the layer off of it, and now the thing below it is a whole different energy level. It's a whole different principal level. So that makes sense, right? Like that's why a cation would be smaller than its original element. And we can see the same thing if we talk about anions. Say, for example, we talk about chlorine. We'll say chlorine looks kind of like this. When chlorine becomes an ion, let's see, it's 3s2, 3p5. When it becomes an ion, it's going to become much larger because it has more electrons around it now. Its new electron configuration, this got a little sloppy, excuse me. Its new electron configuration is 3s2, 3p6. Now, again, it's because we're piling more electrons onto that outer layer. But it also has something to do a little bit with what we would call nuclear charge. So nuclear charge is this idea where it's the charge on the nucleus, right? Remember that each proton on the nucleus has a charge of 1. So chlorine has 17 protons in its nucleus, which means it has a nuclear charge of about 17, right? It has a plus 17. Now, all of those protons are attracting those electrons around it. And in regular chlorine, it has a plus 17. In regular chlorine, each one of those electrons, it's a 1-to-1 ratio from electron to proton. So the protons pull those electrons towards the middle pretty well. But now when we're looking at chlorine with a negative, we have one extra electron on the loose. And our positive charge on the nucleus is the same, which means that it is harder for those protons to get a wrangle on those electrons because we have an extra one kind of floating around in the mix. It's another reason why the size changes when we go from electron to, or when we go from anion to a neutral thing. And the same could be true for sodium. Sodium has 11 protons, so it has a nuclear charge of 11. In regular sodium, those protons are 1-to-1 with the electrons. I got 11 protons, 11 electrons. They're all pulled towards the middle. But with Na+, I have less protons now, which means I have, less electrons, which means I have more protons to handle all of those electrons. I can pull them tighter towards me. Also makes sense. So both are good explanations as to why the size changes. Now understand that these two things, well, these two aren't, but anything that has the same number of electrons in them are isoelectronic. So if we're talking about size, comparing things that are isoelectronic, let's say that we're looking at sodium, right? Let's look at sodium again, Na+, which has a electron configuration of 2s2, 2p6. And we're also looking at something that it's isoelectronic with. We'll look at fluorine. Fluorine also has a 2s2, 2p6. So you might think to yourself, well, how am I supposed to tell which one of these is larger, sodium or fluorine? They're both isoelectronic. You might think, well, sodium's on a lower energy level, but sodium is not in the third energy level anymore. They're both at the same energy level. So when we're talking about isoelectronic elements, this is when we have to think about nuclear charge. I'm going to write that term down so you have it. Nuclear charge. Nuclear charge is the idea of the number of protons in the nucleus. So again, sodium has a nuclear charge of 11, fluorine has a nuclear charge of 9, which means that fluorine doesn't have as many electrons to pull things down with. Sodium has more. So that means if sodium has more things to pull down with, between these two, sodium is smaller. Because they have the same number of electrons, but sodium has more protons to pull those electrons towards the middle. Sodium is smaller. So when we're talking about things that are isoelectronic, we have to consider a nuclear charge. Okay? Now, let's talk about our next trend, ionization energy. Ionization energy is the amount of energy required to remove something from an electron, or remove an electron from 1 mole of gaseous atoms, which means that it's the amount of energy required to pluck an electron off. Negatively charged atoms, meaning things that are on the right side of the table, often have really high ionization energies because they do not want to lose electrons. Whereas things on the left side of the table, left of the zigzag, most cations have a pretty low ionization energy, which means that not a lot of energy is required to remove an electron because they're okay with giving up electrons. Now, the first ionization energy is always the easiest one to overcome. We can always pluck off 1 electron. Sometimes it's hard, but if we are talking about ionization energies, the first ionization energy is always the lowest. The analogy that I like to think about when we continue on with this, because as we continue, we notice that the second ionization energy requires even more energy. The trend is here that each successive energy requires more and more than the preceding. The trend that we often relate to is something like this. The first ionization energy is always less than the second ionization energy, which is always less than the third. It doesn't really matter what we're talking about. The ionization energy for sodium is really low. Sodium is really comfortable just getting rid of that electron. But the first ionization energy is always going to be lower than the second. Sodium's fine with giving away 1 electron, but it's not going to be as comfortable giving away 2. Just something to keep in mind. The analogy that I always like to relate this to is like, say that you're at lunch and you have a bag of chips. And you're just kind of chilling with your bag of chips. And your friend reaches into your bag of chips and takes 1 chip. Now, you'd probably be pretty okay with that. Maybe you would be bothered by it. But it's not the biggest deal. But as soon as your friend comes in and is going for another chip, maybe you let him get away with it. But as soon as your friend comes in for a 3rd chip, now things start getting serious, right? You're putting the bag towards you like, hey, whoa, these are my chips. It's the same kind of analogy here with electrons. The more electrons that we pluck, whether they are willing or otherwise, the more electrons that we pluck from elements, the harder it is to pluck them off. And this kind of lines up again with our idea about nuclear charge, right? The more electrons I remove from the outside, the tighter the protons can hold the remaining electrons. That's a relationship between the electrons and the protons. So that relationship is really important. Now, if we're talking about just general trends, ionization energy increases as we go up into the right, meaning that fluorine has one of the highest ionization energies. or excuse me, I'm sorry, I'm thinking of electronegativity. The noble gases have the highest ionization energy because the noble gases are the most resistant to removing electrons because they want to keep that full set of electrons around them. Now we have a new idea that we call electron affinity. Electron affinity is the amount of energy released when one electron is added to 1 mole of a gas. But I want you to kind of think of electron affinity in another way as well. I want you to think of it as attraction. Electron affinity is how well something attracts an electron. Let's take fluorine, for example. So just to keep the trend, electron affinity lines up with ionization energy. It goes up and to the right. But let's look at fluorine. Fluorine, if we open up fluorine's orbitals, it has a 3s, right? 2s, excuse me. It is a 2s, and then it has that 2p, right? 1, 2, 3, 4, 5. And let's also think about fluorine's neighbor. Let's think about oxygen. Oxygen, which also has a 2s, and it has a almost identical 2p, except it has 1 less electron in the 2p. So if I were to ask you to compare the electron affinity between these two, remember that electron affinity is attraction. It's like how well it attracts something towards it. If this is the case, which one of these is going to be quicker to fill up its empty orbital? Well, fluorine is, right? Because fluorine only has 1 vacant spot. Fluorine's going to be pretty rabid about it. It's just going to take that electron wherever it can. It's going to find it. You can't really stop fluorine from doing so. Oxygen's going to work really hard to do it also. Understand that oxygen is highly electronegative, and it's going to take electrons. But it's not going to be as quick about it as fluorine is. Fluorine has a higher electron affinity, and affinity means that it has a higher attractive rate for electrons. And that's really what we need to look at. So there is a value that you can assign to this, but the value isn't as important to us as the concept behind it. So again, it's its ability to bring electrons in towards it. So all these things that we discussed are factors that we have to consider when we're talking about trends. So first things first, principal energy levels. Energy levels affect lots of things. And when we're talking about energy levels, we mean like, say, for example, sodium and potassium. Sodium is on the third energy level, whereas potassium's on the 4th. Those energy levels factor in a lot of things into all of these different trends. Another thing we need to talk about is the positive charge on the nucleus, which is that nuclear charge I was talking about before. The nuclear charge indicates how hard we pull electrons towards us. So we need to make sure that we mention nuclear charge. And we also want to talk about something called shielding. Shielding is this idea that the more electrons I have in the center, the harder it is for me to have attractive forces on the electrons on the outside. Imagine potassium. Let's talk about shielding. I'm going to put a little asterisk right here, and then I'm going to talk about shielding over here. Imagine potassium. And potassium's got that 1s, it's got that 2s, it's supposed to just be a circle, 2s, and it's got that 3s. We'll call this sodium because I don't want to do a 4s. Let's talk about sodium again, right? So this is the 1s, the 2s, and this is my 3s. If we imagine that sodium is in the middle there, that's the nucleus of sodium. It needs to have enough energy to have attractive forces that reach the first energy level, the second energy level, and the third energy level. But in order to reach out to that third energy level, it's getting blocked by the first and the second. So that's what we call shielding. So in other words, if things have a different energy level, they have different levels of shielding. Sodium would have a stronger shielding than, say, for something like potassium. Potassium has 4 walls to get through. So its shielding is going to be weaker because it's got to get through all 4 of these to get to the outside. Sodium has a stronger shielding because it has a different energy level. Continuing on, these sorts of things that we're talking about here, we need to always try our best to mention them when we are discussing trends. Now understand that when I say always mention them, that doesn't mean that they always point to the right answer. It's just that we always have to mention them. Sometimes these things aren't enough as evidence, and we need to continue to talk about different things. And that's when we talk about things like interelectronic repulsions, and we talk about things like sublevels. So interelectronic repulsions would be kind of like what we were talking about before, where we are talking about the relationship between electron to electron. If we look at two different orbitals, we talk about an example here. If we look at two different orbitals, let's say that we're looking at one that looks like this. This is the p orbital. These are two different p orbitals. We have one p orbital that looks like this, and we have another p orbital that looks like this, right? Which one of these would be easier for us to add an electron to? You would have to say the second one, because I have all this free extra space. That allows me to add an electron to it easier, which means that maybe if I'm discussing something like electron affinity, this would have a higher electron affinity than the first one, because the first one has to put an electron here. And the electrons, they like to be together, but they also don't like to be together. They would prefer to be alone if they could. I mean, they're both negatively charged. So that has a lower level of electron affinity based on interelectronic repulsions. And then sublevels, again, say for example that I wanted to add electrons to something, but I have something that's in the s orbital that has a full s orbital as compared to something that has a 1s orbital. We're telling you like which one of these could I put electrons into. You would have to say that this one would be quicker to accept an electron, because in order for this to accept an electron, it has to open up an entire new orbital to do it. And that's just not going to happen as well. So that is based on the sublevels in which they are located. Things like that, like those pieces of evidence are sometimes things that we have to relate. So if I were to look at these, I would label these as sometimes. So sometimes mention. That should be sometimes, but I ran out of room. So, so these are sometimes mentioned. Sometimes. There you go. So let's look at an example. In other words, that when we're looking at trends, we want to make sure that we at least answer 1 through 3. Let's set an example so we can see how this works. Let's look at lithium versus sodium. And what I would encourage you to do when you're working on this is you're going to be just kind of like writing out a paragraph, but just try and stay as organized as you can. I'm going to go through each question and see if I can answer this thoroughly by looking at lithium and sodium in their atomic size. But before we do that, let's just decide for ourselves which one's larger. Sodium is larger. It is lower on the table. So we know that sodium is larger. So now that we know that sodium is larger, let's take a second. Let's explain ourselves. So let's start at number 1. Let's talk about the principal levels where the valence are located. Let us start plainly first, though. Let us say Na is larger than Li. And now that we have that, let us start talking about why. So we're talking about principal energy level first. Remember that if you think about it, Na has more layers of its onion, right? So all we really need to say is that Na is at the third principal level. I don't think I'm spelling that right. Principal, there we go, principal level. While Li is at the second. So that's all we have to say. That implies that there are more layers to sodium. Now let's talk about number 2. Number 2 says, let's talk about the positive charge on the nucleus. What are the positive charges on the nucleus? Sodium has a plus 11 on the nucleus. Lithium has a plus 3 on the nucleus, right? So lithium doesn't have as many electrons and it doesn't have as many protons. So when we're talking about things on different energy levels, like completely different energy levels, sometimes the nuclear charge isn't the most important thing, but we can still state it. We can say Na has a plus 11 charge on the nucleus, while Li has a plus 3 charge. And we can add a little bit. We can say meaning. Oh no, let's just leave it there. Let's not change our answer. So again, this isn't something that's actually pointing towards the evidence very well, but we still need to state it. For 3, we're talking about shielding. Shielding is, again, how many layers that they have, right? Lithium has less shielding. Therefore, it has more access to those outer electrons. So we'll say since Li is at the second energy level, it has less shielding. It has less shielding than Na, meaning it is smaller. So that's all it takes. We don't have to continue on, and we don't have to talk about 4 and 5 in this situation because it's not applicable to this. But sometimes, again, if we're talking about something like maybe ionization energy, or if we're talking about electron affinity, that's when we need to talk about 4 and 5. Okay? So I would encourage you to do a little practice with this. Try out these examples here to see if you can kind of work your way through it. This is all great practice. Look at these examples and see if you can compare those things and relate them to the different topics that we saw above. And that's it, folks. So we're just taking the trends and we're explaining them further using the knowledge that we've gained from previous chapters. If you need any practice or if you have any sort of questions for me about it, please let me know. I know this can be tricky. This is a analyze sort of scenario. This is not a memorize sort of thing. So make sure that we work together to make sure we're on the same page. We'll see you next time.